Hey everybody, it's Ripley back again. Today we're going to talk about maxes and mins of functions. In other words, maximum and minimum values of functions. Now, we're going to talk about this initially on a closed interval because I think it's more important for us to talk about closed interval functions on closed intervals than it is to talk about functions on open intervals because it can get a little bit tricky. So what I want to show you first and foremost is let's talk about the maxes and minimum values of this function on this closed interval from A to B. All right, so there are two kinds of maxes and two kinds of mins. There are relative, which I will usually abbreviate as rel, or another way to say that is local max or mins. Now, so I can have relative or local max and mins, and then I can have absolute or global. And it depends on your textbook which ones they use. So it's kind of important to look in your textbook, whatever you're using, and figure out what's the sort of nomenclature that they use. All right, so let's talk about this graphically first, and then we'll give you some actual formal definitions. First things first, this guy right here, what would you say that is? Is that a max or a min? Well, it should be relatively obvious that it's a max. It's the highest point here, but is it the highest overall point? Is it the absolute largest point that we have on this interval from A to B? And the answer to that is no. So this is a relative max. Typically, you'll say relative. You don't hear local as much anymore, but I want to make sure that you have that. So this is a relative or a local max. Likewise, this is a relative min. Now, why is this relative and not absolute? Well, because all of these values down here are less than this value, just like all of these values up here are greater than this value. How about this one? What's this? Well, I don't know what that is. Let's get rid of that. What is this value up here? Well, this is the biggest value on the closed interval from A to B, isn't it? So this is an absolute max. Last but not least, we got this point down here. What's this? Well, even though, and you may say, well, oh, Ripley, I'm starting to see a pattern here. This is kind of where functions level off, right? Well, not necessarily, especially on a closed interval. So if I've got this guy down here, this is definitely the lowest value, the most negative, well, the smallest value of the entire function on the interval from A to B. So this is an absolute min. All right, now there's this question that's begging to be asked. What do we do with this? Now you may say, well, it's less than or equal to all of the values sort of arbitrarily close to it right here, right? So wouldn't that make it a relative min? The answer to that is no. And that's a frustrating thing because, well, I'm not going to get into it because that's kind of my rant. Suffice it to say that 99% of textbooks will not allow for relative maxes or mins on the endpoint of a closed interval. So this is neither. I know that seems counterintuitive, and there's something that frustrates the heck out of me, which I'm going to show you right now because I think it's important for you to see. Because it's a definitional thing. You got to understand that it's definitional. It has to do with open intervals, which we'll talk about here in a sec. So let's say, for example, I'm just going to deal with the left-hand side. Let's say that this is A. And let's say that I have a function that does this. Like that, okay? Now, this is my function f of x. Now, let's look for just a sec. What do you think, this is a horizontal line, by the way, it's just horribly drawn. This point right here, what do you think that point is? Well, it all depends on our definition of a max or a min. So let's actually formalize that right now. Okay, God bless it, sorry you guys. Well, let's formalize that right now. We're going to say let C be a number in the domain of f. All right, this will imply f of c is, and then I'm going to put colons here, I'm going to say 1, an absolute max if and only if f of c is greater than or equal to all other f of x for every x in the domain. Now we're getting fancy. We're going to call this, maybe I should put a capital D here, parenthetically. All right? If f of c is greater than or equal to all other f of x for every value of x in the domain. Remember, this upside down capital A means for every. This guy means an element of. 2 is an absolute min, if and only if f of c is less than or equal to f of x for every x in the domain. Now that makes sense, doesn't it? Now this is a robust mathematical statement about an absolute max and an absolute min, but we already knew this intuitively and graphically, right? It wasn't very hard. All right, now how about a local max? So let's go 3 is a local max if and only if f of c is greater than or equal to f of x for every x near. Now this is a weird word. I'm gonna explain this in just a sec. Near x equals c. Now what does that mean? This near, that's a terribly unmathematical way of saying it. Well, what it means is I know that I have a local max if I have a single open interval around f of c such that f of c is greater than or equal to all of that values on that interval. So let me change my color real quick. Let's make it obnoxious so you can see. So let's look at this relative max. If I open up that open interval, then this f of c, let's suppose that that is c comma f of c. I know f of c lives over here, right? So I know that f of c is greater than or equal to all of the values on that open interval. That is the way of saying near. Now you may say, wait a second, Ripley, but that appears to be greater than or equal to a whole bunch of values. Well, yeah, it's true, except if I open up this open interval, watch what happens. Well, now this value right here is greater than or equal to this value. So that implies that this cannot be an absolute max because it's got values that are greater than. It is a relative max if and only if there exists one open interval such that that value is greater than or equal to all of the values on that open interval. Okay, let me change out of this puke green color. 4, it's a local min if and only if f of c is less than or equal to f of x for every x near x equals c. Okay? In other words, now down here, likewise, right? If I open up an open interval around it, every value on that open interval is going to be greater than or equal to this relative min. But if I get big enough, then I get over into these values. Okay? That's the definition. Now, if you use that open interval definition, it's a lot easier to explain why I cannot have a relative min over here, because I can't open up an open interval around the point. Whoop, whoop. I can open it, I can do a one-sided, I can do a half open interval, but I can't do a truly open interval. And that's the reason that we say that at endpoints you can't have relative maxes or relative mins. I know it's confusing, and it's about to get more so. So here's why. You ready? Let's look at this example that I drew down here. We're just going to deal with f of x from A to who cares over yonder, okay? Now, let's look at this point right here. So I'm going to call, I'm going to call this point right here c comma f of c. Now, do you agree that if I take an open interval around c f of c, that this point is greater than or equal to every value in that interval? So this point right here would be a relative, well, however, how this thing is drawn, this would actually be an abs max, right? It's the absolute maximum value of the function. Okay, now here's where it gets crazy. Oh, you guys are going to hate me. What about this value? Now, again, assume that this is a horribly drawn horizontal line. What would this value be? Well, it's exactly the same value as c f of c because it's a horizontal line. So it has to be an absolute max, an abs max, right? Because it's greater than or equal to all of these values down here. It's also greater than or equal to all of the values in that open interval that I just opened up. Now, here's where you're going to lose your mind. It's also a relative min. Why is it a rel min? All right, it's both of them. Okay, well, it's the equality that screws us up. This open interval, for this open interval, this point right here, which I could just call d comma f of d for lack of a better word. That's a little confusing with this big D in domain, but let's not worry about that. this equality is what jacks everything up. D f of d, that point f of d, this value f of d, sorry, f of d lives over here, is also less than or equal to all of the values in this open interval, which makes it a relative min. So it can be both an absolute max and a relative min. Now, you must realize that this is an exceptional case because I have this horizontal line, right? This function is horizontal for these values. Now, this is going to make it even crazier. You should see that if I go just left of c, if I go just less than c, then all of the function values are going to have this crazy property of being an absolute max and a relative min. Guess what happens when I hit AF of A? Well, AF of A, it is, now this is where it gets crazy. I am not allowed to have a relative max or min in an endpoint. So I have a relative, or excuse me, I have an absolute max still. But I lose my relative min because I'm not allowed to have relative maxes and mins. Now here's where it gets even crazier. And this is where we tie ourselves in knots with definitions. If f of x, if f of x goes down here and then comes back up here, okay? So over here at a f of a. Now, what would that change? Well, at cf of c, instead of having an absolute max, I'd have a relative max. I can't have a relative min because it is not less than or equal to, because these values down here are not equal to, okay? All of the points along here would still be relative maxes and relative mins. I'd lose that absolute max because all of the values on the function over here are larger than all of the values here. So I would have a relative max and a relative min for all of these. So this is, this guy's, this is getting hard to write on. Instead of abs, this becomes relative max only. Can't be a relative min because these values are less than it. All of these, I'm still going to have a relative min, but I'm also going to have a relative max. And guess what happens to that point? Because it's an endpoint on a closed interval, and these values are greater than it, right? I cannot have a relative max or a relative min, so I lose everything. We have twisted ourselves in a definition knot, which drives me crazy, but I want to be consistent with all of your textbooks. So just realize that on an open interval at the endpoints, you cannot have relative maxes and mins. Also, you can create some pretty strange functions if you're not careful, right? Where you get values that are both relative maxes, relative mins, absolute maxes, relative mins, etc., etc. Okay? Now, we've looked at this graphically. Now, which is nice, and then we've sort of robustly defined what it is to be an absolute max, or a relative max, or local max, local min, local, yeah, blah, 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 okay? Notice I wrote local, which is weird because I learned in a textbook they called it a local max as opposed to relative. So these, remember, these can be referred to as global as well as absolute value, or excuse me, as well as global, as well as absolute, and these can be referred to as relative. So just watch out for the vocab because it can get a little confusing. All right, cool. Now let's talk about another value theorem. We already talked about the intermediate value theorem. We got the IVT. Now we're going to talk about the extreme value theorem, which is super helpful. Extreme value theorem. Okay, and the extreme value theorem is really simple. It simply says, suppose f is continuous on a closed interval. It starts the same way as the intermediate value theorem. On a closed interval, let's go A, B. All right? If f is continuous on a closed interval A, B, then there exists, this implies, there exists both an absolute max and an absolute min on the closed interval from A to B. There has to. It makes sense, right? It's continuous. So there are no jumps, there are no skips. So from A to B, right, as long as there's no hops, there's no vertical asymptote, there's no nothing crazy going on, in other words, it's continuous, then I have to have both an absolute max and an absolute min on that closed interval. So you have your second of your extreme or of your value theorems, and this one's really important when we start playing around with the applications of differential calculus, because it enables us to do some interesting things and it lightens our burden computationally. Life gets a lot simpler when I have the extreme value theorem. Okay, I'm going to meet you on the next page here in just a second, and we'll talk about some applications of the extreme value theorem and our understanding of these maxes and mins. All right, see you. Okay, so the extreme value notwithstanding, we still have to look at functions that aren't necessarily continuous and determine whether they have maxes and mins on them, right? So again, let's just putz around with a little closed interval here just to keep things simple. This is going to be A and this is going to be B. And let's say that I have a function that does something like this. And then I've got this vertical asymptote here. And then I've got a function that goes like this. I know this is an asinine function, but whoop, open interval there, and I pop this guy up. And then I go over here. Now, let's just look at some stuff. So first and foremost, what do we know about this point right here? Well, it's on an endpoint. So it's either had to be a max or a min. It's either got to be an absolute max or an absolute min, which it clearly isn't. So nothing doing here. How about this guy right here? How about this value? Well, that is definitely a relative max, but is it an absolute max? Well, no, because this guy right here is bigger, even though this is not a continuous function for a number of reasons, right? Not least of which is the vertical asymptote cutting right down the middle, and then this guy over here. So this would be a rel or a local max, right? And then how about this guy over here, this other endpoint? Nope, same problem. It can't be a relative min because it's on the endpoint of a closed interval. Oh, excuse me. Now, students will often say, let me do this with color. Let's start here. It should be relatively obvious that this is the absolute max. This is the global max. It's the biggest that the function should be. But Ripley, what about the extreme value theorem? Well, the extreme value theorem doesn't mess with the definition of absolute and relative maxes. It just says that if you have a continuous function on a closed interval from A to B, you have to have an absolute max and an absolute min. Well, this is not a continuous function. So we're not invoking the extreme value theorem, so we don't worry about it. Now, students will ask me, like, what about this point? What about the point right there that's really close? I'm going to do that in kind of, we'll do it in a little sidebar over here. Okay, so here's my value. For any value that I pick, or excuse me, there's my hole. For any value that I pick, say here, right, it should be relatively obvious that that is neither a max nor a min because the values to the right are greater, values to the left are less than. Well, what about right there? Now remember, this is an open hole. So if I go here, well, I can just do this whole thing again. It's just that the hole gets bigger, and now I've picked this value. I've got an infinite number of values that are greater than it and an infinite number of values that are less than it. We'll get even closer. Well, we just keep scaling this thing out. The hole gets bigger, the point gets closer, but I still have an infinite number of values that are greater than and an infinite number of values that are less than. So what this hole produces is an inability to ever get to that value, because if we could, then we wouldn't have a function. And if I'm just getting arbitrarily close, well, I end up in this situation where I can continually open smaller and smaller intervals, wherein those intervals have values that are both greater than or less than the point. Okay? Okay, now, I am about to give you the keys to the kingdom. I'm going to give you something called, the Ripley-Doodle diagram. And then I'm going to use the Ripley-Doodle diagram. The Ripley-Doodle diagram. This is my diagram, my megalomaniacal way of getting my names in the annals of mathematical history. All right, so I'm going to show you how to use this new tool, and then I'm going to cover one more theorem, and then we'll be done for the day. All right, so here's what a Ripley-Doodle diagram is. It is a sign chart. That's all that it is. But we're going to use the heck out of it. But I want to do this. Let's do it with the function. What we're going to do is we're going to determine all maxes and mins of a specific function. Let's let that function be, let's go x cubed minus, let's go 3x squared plus 2. And let's do it on -1 to, say, 4. Let's go 1 to 5. Okay? All right, Now, as I work my way through this, we're going to come up with some definitions that we're going to use. Probably the most important term that you're going to pull out of this section is something called a critical value or a critical point. Critical point can be a little misleading. A critical value. All right, a critical value is simply an x value such that f primed at, you know what, let's go, I'm going to do this parenthetically. I'm going to call it c. All right, so it's an x value, but we're going to call it c, such that f primed of c is either equal to 0 or f primed of c does not exist. That's why it's critical. Now think about what it means to have a max or a min. Well, if I'm going to have a max or a min, if the function is differentiable, if the derivative exists, and I want to talk about a max or a min, then what does the derivative have to be? Well, let's look here. Well, guess what? Levels off, levels off, levels off, levels off, levels off here, does not exist there, right? Even over here, this is a leveler off, this is a does not exist. The derivative doesn't exist there. Okay, so that's why it's called a critical value or a critical point. But what that gives us is this wonderful starting place when we're doing, or the starting point, no pun intended, when we're going through these types of problems. So what I'm always going to do is the first step, if I'm looking for maxes or mins, is always to take the first derivative, which in this case is 3x squared minus 6x, right? The 2 goes to 0, and set it equal to 0. Because if I'm going to have maxes and mins, they're going to always be at critical values, places where the first derivative equals 0, or places where they don't exist. There's a theorem that we'll talk about called Fermat's theorem that talks about this very phenomenon, okay? All right, so if I set it to 0, this should be relatively obvious. I take x, pull out my 3x, and I get x minus 2 equals 0. Now we actually want to take the step right here. I say critical value at x equals 0 and 2. This step, if you're in my class, I'm going to grade you on that. I'm going to make sure that I see this every single time, okay? And I slap this bad boy on f prime, and I have to label it. If I don't label it, I get confused. I don't know where I'm plugging values into, whether it's the derivative or the function itself, the mother function, and I can get really, really confused, okay? Now, on my Ripley-Doodle diagrams, if I'm talking about a closed interval, I actually put those on there. It keeps me honest. I'm going to put only critical values. Only critical values go on a Ripley-Doodle diagram. Nothing else belongs on a Ripley-Doodle diagram. Otherwise, you will get confused and you'll think that not critical values are indeed critical values. So I'm going to put a 0 here and I'm going to put a 2 here. Notice I don't put a 1 here, or I don't put 3s and 4s here. In other words, you don't have to enumerate your Ripley-Doodle diagrams. All you need are endpoints of closed intervals, if you have them, excuse me, and critical values. Otherwise, it gets confusing. Now watch. This is the great part. Very much like what we did before. Remember when we were talking about particles speeding up and slowing down back a few sections ago? Very much like that. I don't care about actual numbers. I only care about values being positive or negative. Pick a value between -1 and 0. Let's call it -0.5. If I plug that into here, I get a negative. If I plug it into here, I get a negative. Negative times a negative is a positive. Pick a nice little value between 0 and 2. Let's pick 1. Plug it into here. Plug it into 3x, I get positive. Plug it into x minus 2, I get a negative. Positive times a negative is a negative. If I plug in a value between 2 and 5, I like 3 or 4. Let's put in 3. Throw that in here, I get a positive. Throw that in here, I get a positive. And guess what? I get a positive. Now here's the coolest part. This Ripley-Doodle diagram, because I've labeled it as a first derivative and it's sitting right there, I know that it tells me when a function is increasing or decreasing. Right? If the first derivative is positive, my function increases. If my first derivative is negative, my function decreases. Right? Because the slopes of lines tangent are positive and negative. You see what we're getting at? This is really, really important, and it's also super, super helpful. I will elaborate further on this in the next section, but for now, just know when you got this Ripley-Doodle diagram, if the first derivative is positive, my function goes up. I had a critical value at x equals 0. That was when the first derivative equaled 0, so it's got to level off. From 0 to 2, excuse me, from 0 to 2, the first derivative is negative. down I go. At 2 it levels off, and up I go. So I have a stick figure of a function. Now, I know that this guy right here is going to be at least bare minimum rel max. And I know this guy here is going to be at the bare minimum a relative min. But I can easily check that. All I have to do is plug in f of -1, because I got it. Remember, I still always check your endpoints. The rule that the extreme value theorem gives us, and maybe I should put that, you know what, I'm gonna put that right over here. I'm going to imply, even though this doesn't necessarily imply, let's not use an implication. I'm not mathematically implying something. I am saying always check endpoints. Always. Always, always, always. On a closed interval. If you have a continuous function on a closed interval, always, always, always check your endpoints. All right, because they can be absolute maxes or absolute mins. I realize they can't be relative maxes and relative mins, but they can still win the game, as it were, okay, in terms of being an absolute max or an absolute min. All right, so let's look at this. F of -1 is going to be -1 minus 3 plus 2. Remember, I'm just using this function over here, which is -2. I know that f of 0 is going to be 2. I know that f of 2 is going to be 8 minus 12 plus 2, right? Which is what? -4 plus, that's -2. And then I've got f of 5, oh good Lord, which is going to be 125 minus 75 plus 2. That looks like 52, doesn't it? It might be, yeah, that's right. Let's make sure that's right. 325, yeah, I got it. It's 52. Now look at it. I know f of 0, this guy right here, since f of 5 is 52, and look, there are no other places where the first derivative equals 0 or doesn't exist. So these are the only candidates for absolute and relative maxes and mins, right? So let's just go through it. Well, this guy right here, let's change my color, draw attention to it. This guy right here is the abs max. It's got no choice. This guy right here is a relative max, right? This guy right here is going to be what? Well, check that out. That's kind of crazy. At f of -1, which is at the endpoint, I got -2. And f of 2, I got -2. Let me make sure that's true. A, -2. Yeah, I'm good. So these are both absolute minima. Minima is just it's plural for minimum. Optima is plural for optimas. And this is going to be the abs min as well. Now you got to be really careful. Just one more little addendum to all of this. In the problems, you have to read, you have to make sure that you answer the question, which means you have to read the question. If the function were to, or excuse me, if the problem were to ask me, where on the function f of x equals x cubed minus 3x squared plus 2 do we have maxes and mins? Well, that implies what are the x values for which we have maxes and mins? And we would say, well, we have absolute max at x equals 5, absolute mins at x equals -1 and 2, and relative max at x equals 0, right? That's pretty easy. But if it says, what is the maxes and mins? Then I would have to say, well, the absolute mins are at -2, is -2. The absolute max is 52, and the relative max is 2. A way around this to sort of always stay out of trouble, well, not always stay out of trouble, because if I distinctly say, give me the x values for which we have maxes and mins, then you would say -1, 0, 2, and 5, and then tell me whether they were maxes or mins. But one way to always think about it is to present your values as points. So I can say, I can go -1, -2, 2, comma, -2. These guys are abs min, right? And then 0, comma 2, this is a rel max. And then 5, comma 52 is an abs max. Okay? All right, that's it. Okay, so be careful. Make sure that you read the problem. Make sure that you answer the problem correctly. The best skill that you're going to take out of this lecture probably is the use of the Ripley-Doodle diagram. It's super, super helpful. For those of you that are preparing for the AP exam, know this. A Ripley-Doodle diagram cannot be used as justification. You can use it, you just can't use it to justify your position. But that's easy enough, right? I mean, think about it. If I had to prove that something is a max, I would simply say that the function increases and then decreases. If I had to prove that it was a min, I could simply say it decreases and then increases, which is easy. I could also use something like this to say. We know by the extreme value theorem that if I had any other hoopty-doopties that produced maxes or mins, then it would show in the derivatives, okay? But let's burn that bridge when we get to it. When we start getting into AP prep stuff with your instructors, then you can start parsing out the finer points of that, okay? All right, one last thing, and then I will be done. Let's talk about Fermat's. I don't know why I did that in lowercase. Let's talk about Fermat's theorem. Fermat's theorem. And it's really simple. It simply says if f has a local max / min. Now, remember, a local max, okay, this is where it gets a little confusing. An absolute max, if we go back and look at our definitions, this won't take but a second, so bear with me. An absolute max is greater than or equal to f of x for every x. A relative max or a local max is greater than or equal to x very near c. Okay? So if I have an absolute max for nothing, by default, I know it's also a local max. So all absolute maxes are also local maxes unless they're on an endpoint, because endpoints of closed intervals cannot be local maxes or mins. Likewise, if I have an absolute min, it is by definition a local min, unless it's on the endpoint. For example, this guy, this absolute min that we had over here. All right, this is definitely an absolute min, but it can't be a local max because it's on an endpoint, which kind of sucks. They're kind of prejudiced against endpoints, apparently. All right, oh, look, it turned into a thing again. All right, it says if f has a local max, min, excuse me, at x equals c, and f prime of c exists, this implies that f primed of, of c, that's a single prime, f prime, wow, Ripley, sorry, my caffeine's starting to wear off apparently, f primed of c must equal 0. It has no choice. Now, this says if f primed of c exists, then f primed of c is equal to 0. There's no guarantee. Remember this ding-dong right here? This guy was an absolute max, right here. This point, whoop, right there was an absolute max. But the derivative didn't exist, so I can't invoke Fermat's theorem. That's not his last theorem. Let's not confuse that. All right, basically all this says is, hey, guys, this is, I don't know how old this is, probably 400 years. This basically says, hey, if you're, no, it can't be 400. Well, anyway, it doesn't matter. If you're going to use derivatives, you might as well set them equal to 0 first and see what plays out. Even if it doesn't equal 0, then you're going to be able to tell by the derivative where it doesn't exist, and you'll still get critical values that you will then test. Like, for example, if I let f of x equal the absolute value of x. Well, when I take the derivative of this, remember this is equal to x. Let's go negative x for x less than 0 and x for x greater than or equal to 0. We know what it looks like, right? It's the v. And then this is the absolute value of x. Well, we have an absolute min right here at 0, 0. But we also know that this guy is not differentiable at 0. The derivative from the left and the derivative from the right are not the same. All right, remember it's got a point. We talked about that before. So again, since f prime of c doesn't exist, I cannot invoke Fermat's theorem. But I know that there's an absolute min there, just visually or algebraically or graphically from what I've known with absolute x. So when I take the derivative of this, I'm going to get a critical value at 0. I don't have a choice because it's non-differentiable. So at least, even if you can't use Fermat's theorem, at least using the first derivative, setting it equal to 0, and then using things like Ripley-Doodle diagrams and finding critical values is super helpful. It's also very organized. It's a great way to have your work organized, which we will get into a huge part in later sections. We want to keep our work very, very organized. We want to be methodical about what we do with our work. Okay, that's enough of me yapping at you. Hope it was helpful. Have a wonderful day, and I will see you in the next section.